Hi, and welcome to a new lesson from Easy Chemistry. This is Mr. Kosai, and today we're going to continue what we started in the previous video about the acids and bases. Today we're going to focus on the diprotic and triprotic acids. We're going to solve some problems about these acids in terms of the concentrations and the pH. These are some examples about the polyprotic acids. That means they have more than one proton in their structure. For example, we have the H2SO4, we have the H2CO3, and we have the H2S. Before we start solving the problems for the concentrations and the pH for these kinds of acids, we need to understand what are those polyprotic acids. These polyprotic acids may yield more than one hydrogen ion per molecule. As you can see, those acids, they have more than one hydrogen ion, so they can yield more than one hydrogen ion per molecule. Also, they ionize in stepwise manner. It means that they lose one proton in each stage or in each step. The ionization constant expression is written for each ionization stage. That's why you will find that we will have Ka1 and Ka2, and if we have a triprotic acid, we will have Ka3. Also, two or more equilibrium constant expressions must often be used to calculate the concentrations of species in the acid solution. All right. Let's have some examples about those polyprotic acids. For example, we have H2S. H2S is a weak acid, and it ionizes in two steps. For the first step, it's a reversible reaction, and it will give you H positive plus HS negative. And we have a Ka1 for this step. Then HS negative also will decompose or will ionize in a reversible reaction to give you the other proton plus S negative 2, and we have Ka2 in this case. H2SO4 is a very strong acid, so the first step is not reversible reaction. It decomposes it ionizes 100% to give you the H positive plus HSO4 negative 1, and we don't have Ka because this is a complete dissociation for the sulfuric acid. Recall, guys, if you haven't watched the first video about the acids and bases, I recommend you guys to go and watch it before we continue. Now, the second step is HSO4 negative, which is a weak acid, so it ionizes in a reversible reaction to give you the other proton plus the SO4 negative 2, and in this case we have the ionization constant expression, which is Ka. Similar thing for the sulfurous acid, weak acid, oxalic acid, and the carbonic acid. I want you guys to try to write the equations for each acids of those three. All right. Let's check now example problems about those polyprotic acids and how we solve for the pH and for the concentrations. Calculate the pH of 3 molar. Actually, this one was wrong. It should be 0.3 molar H2SO4 solution. And the Ka for HSO4 negative is 1.2 times 10 to the power of negative 2. All right, so this is before we start, I want just to tell you about this. A lot of students, they make mistakes in the exam. What they do is, we know that the pH is equals to negative log the concentration of H positive, and right away they find, all right, we have here the concentration, we use the pH, negative log the concentration of H positive, because HSO4 is a strong acid, without doing the ICE table. And the mistake is that they put the 0.3, the concentration of the acid, which equals to the concentration of H positive, right away, and they find the pH, which is incorrect. This is a diprotic acid, not monoprotic acid, just like HCl or HNO3. So in this case, we have two steps, as you found. The first step is to write the initial acid, which is H2SO4, and this is a very strong acid, so it ionizes 100% to give you the H positive plus the HSO4 negative 1. Because it's strong acid, so the initial concentration of H2SO4, it equals to the concentration of the proton or the hydrogen ion, and also for HSO4 negative 1. So this is for the first step, which is a strong step, because H2SO4, we know that it's a strong acid. Now, the second step is, what about this one? It will also ionize to give you the H positive. So we're going to write it HSO4 negative, but in this case, it's a weak acid. So the reaction is a reversible reaction to give you the H positive plus SO4 negative 2. And in this case, we have a Ka for this step. Now, we need to use the ICE table, just like what we did for any weak acid. Using the ICE table, what is the initial concentration of HSO4 negative? It's right here. It came from the strong acid. So this is the initial now. So the initial concentration is 0.3 molar. And the initial concentration also of H positive is 0.3. And the initial concentration of SO4 negative 2, we don't have this species in the first reaction, so it's going to be 0. In the change, because the HSO4 negative is being consumed, is being ionized, so it's going to be negative X. H positive is being produced, so positive X, and SO4 negative 2 is also positive X. In the initial, we add the I to C, so it's going to be 0.3 minus X, and here we have 0.3 plus X, and here we have X. Now, we need to write the constant for the ionization constant for this reaction. That means Ka equals to the concentration of the products divided by the concentration of the reactant, which is HSO4 negative. And we already have it, which is 1.2 times 10 to the power of negative 2. So 1.2 times 10 to the power of negative 2 equals to, here we have the H positive at equilibrium is 3 plus X, 0.3 plus X multiplied by X divided by 0.3 minus X. Now, before, to make it easier, we used to say, all right, X is very small amount. That means it's a negligible amount. That means 0.3 plus X almost equal to 0.3. And 0.3 minus X also almost equals to 0.3. So this one is 0.3, 0.3. So they cancel each other, leaving X only. So X equals to, in this case, 1.2 times 10 to the power of negative 2. But not in all cases what we can do. We need to check something called the ionization percentage, which is we take X and we divide it by the initial concentration of the acid, which is here 0.3. So I'm going to divide it by the initial concentration of HSO4 negative, and we're talking about percentage, so I need to multiply it by 100. Now, the rule is if it equals to, or the product here is less than 5%, then we can neglect X and we can find X equals to 1.2 times 10 to the power of negative 2. But if it was greater than 5%, we cannot do this, and we need, unfortunately, to do the quadratic equation. So let's check here. We have 1.2 times 10 to the power of negative 2 divided by 0.3 multiplied by 100 equals to and in this case it equals to 4%, so we can neglect X here, and this value is acceptable. Again, what did we do? After we found X, we divided by the initial concentration of the acid and we multiplied by 100. If it's more than 5%, we cannot neglect X and we need to do the cross multiplication and we solve for a quadratic equation. If it was less than 5%, I mean, then this X, after we neglect X from this equation here, we can accept this value. So I'm going to accept this value, and X now, it equals to 1.2 times 10 to the power of negative 2. Now let's solve it for the H positive, because in the main problem here, they're asking for the pH. Now we have X, and therefore the H positive, it equals to 0.3 plus 1.2 times 10 to the power of negative 2, which equals to 0.312 molar. Now we have this concentration of the H positive, therefore we can use pH equals to negative log the concentration of H positive, negative log 0.312, which equals to 0.5. And 0.5, that means the sulfuric acid is very, very strong. I hope you guys understood this problem, but to make sure that we understand it, let's solve this problem very quickly. Oxalic acid, H2C2O4, is a poisonous substance used as a bleaching agent. Calculate the concentrations of all species present at equilibrium in a 0.1 molar solution. You have Ka1 and you have Ka2. All right, we need to write the first reaction, which is, because it's diprotic acid, so H2C2O4, and it's a weak acid, so it's going to decompose or ionizes in a reversible reaction to give you H positive plus HC2O4, and we have Ka1 for this equilibrium. Weak acid, so I'm going to use the ICE table. The initial concentration for the acid was 0.1. The initial concentration of H positive is 0. The initial concentration of HC2O4 negative is also 0. The change is negative X, positive X, and positive X. And at the equilibrium, 0.1 minus X, X, and X. Now, the Ka1 or step number 1, it equals to x squared, because the concentrations of the products divided by the concentration of the reactants. So it's going to be x squared divided by 0.1 minus x. All right, so let's solve for x. Initially, we're going to neglect this x because it's a very small amount. And we're going to use the Ka1, which is 6.5 times 10 to the power of negative 2 equals to x squared divided by 0.1. And then we do the math. X equals to 0.081. All right, now we need to check the approximation. Can we neglect this x or not? We're going to have x divided by the initial concentration of the acid, which is 0.1, and we multiply it by 100 and we check. That means if we divide it by 0.1 and then we multiply it by 100, it's going to be 81%. So in this case, we cannot do it. That means we cannot neglect x. We're not going to neglect x in this case. And therefore, we're going to write the quadratic equation. After we do the cross multiplication, so it's going to be x squared and then minus, because this is Ka1, so it's going to be minus 6.5 times 10 to the power of negative 2x plus 6.5 times 10 to the power of negative 3, and which equals to 0. So this is the quadratic equation that we're going to use. And we solve for x, which equals to 0.054. I want you guys to check how we solve the quadratic equation. Maybe you can watch some YouTubes, or you ask your teacher about the quadratic equations. So now we have x, and we need to find the concentration of H positive. That means H positive in this step, it equals to 0.054. But we have another step. So we cannot write that the H positive equals to this concentration. We only found X now in this case. And we found X because we're going to use it in the second step of the decomposition, or of the ionization of this acid. Because the second step is going to be HC2O4 negative. Also, it will decompose in a reversible reaction to give you H positive plus C2O4 negative 2. And we have here the Ka2. Also, we need to write the ICE table. Here, you need a little concentration. The concentration of HC2O4 negative is 0.1 minus X. So it's going to be 0.1 minus 0.054, which equals to 0.046, because this is at the equilibrium. The concentration of the equilibrium, 0.1 minus X. And for H positive, it's X. So I'm going to write it here, 0.054 initial concentration for the proton, or for the hydrogen ion. And for the C2O4 negative 2 is 0, because we didn't have any of this ion in the first step. Now, in the change also, the same thing, minus X, plus X, and plus X. The equilibrium now is 0.046 minus x, here 0.054 plus x, and here we have it plus x. Now Ka2 equals to the concentration of H positive multiplied by the concentration of C2O4 negative 2 divided by the concentration of H C2O4 negative 1, which equals to 0.054 plus x multiplied by x and divided by 0.046 minus x. Let's solve it for x. If we neglect these x initially, always we follow this. We're going to neglect these x's, so it's going to be 0.054x divided by 0.046 multiplied by the Ka2. And in this case, after we cancel, we neglect the x, so x equals to the Ka2, which equals to 6.1 times 10 to the power of negative 5. Now, what we need to do is to check the approximate. So we will take this x and we will divide it with the initial concentration and we multiply it by 100. So it's going to be 6.1 times 10 to the power of negative 5 divided by 0.054 multiplied by 100 is going to equal 0.1 0.11%, and which is less than the 5%. So we can accept this value of x. Now, this is x. What is the hydrogen ion in this x? Is going to be the concentration of hydrogen ion in this solution. It equals to 0.054 plus the 6.1 times 10 to the power of negative 5, and which equals to 0.054. See, it's very small amount, but we have to calculate it. So it's going to be equal to 0.054 molar. Next steps is to find the pH, because pH, it equals to negative log the concentration of H positive. That means it's negative log the 0.054, and which equals to 1.2 or 1.3. This is the pH. Don't forget that we can find now the pOH and the concentration of OH negative. Last example, guys, I would like you to have it as a problem solving for you to practice about the diprotic and triprotic acids. I hope you guys learned something new. If you have any question, hit me up in the comments. I will read all the comments. Also, if you want us to focus on another topic, just let me know. As I told you, I'm always reading all the comments. Have a nice day. Bye-bye.